Hidden beneath the ocean's surface are massive, towering canopies. The stalks in these underwater forests can grow up to 20 inches in a single day, eventually reaching heights of 80 meters. But despite looking exactly like towering trees, these organisms are entirely unrelated to land plants. They belong to a distinct biological group known as Stramenopiles. Through a process called convergent evolution, this microscopic lineage faced similar environmental pressures as land vegetation and ended up engineering a nearly identical physical structure to survive in the water. To compete for sunlight in turbulent currents, they developed pneumatocysts. These are specialized gas-filled bladders that act as built-in buoys, lifting the heavy fronds straight up toward the surface. By exploiting these physical adaptations, this organism built one of the most productive, fast-growing habitats on Earth. One of the largest is the Great African Sea Forest. It is a continuous 1,000-kilometer stretch of giant bamboo kelp running from the shores of Cape Town all the way to Namibia. Archaeologists have found evidence here dating back 100,000 years, suggesting this specific coastline was one of the first places early humans actively dove and interacted with the marine environment. Today, the canopy supports an extreme concentration of life. Tiny, plankton-filtering crustaceans called mysids gather in massive swarms, providing a food source that attracts everything from reef fish to 4-meter-long short-tail stingrays seeking shelter. The kelp's natural buoyancy even allows detached fronds to form vast floating rafts. Ocean currents carry these rafts across great distances, allowing diverse hitchhiking species to colonize completely new regions. This massive biological engine supports an entire regional ecology of life, but its scale hides an incredibly fragile internal balance. If we look at the giant kelp forests along the North American Pacific coast, we can see exactly how delicate this balance is. The entire ecosystem is held together by invisible biological strings called a trophic cascade. It operates on a strict 3-part food chain. Sea otters eat purple sea urchins, and purple sea urchins graze on kelp. When an apex predator like the sea otter patrols the water, urchins are forced to hide in rock crevices, surviving only on fallen kelp scraps. This allows the living forest to grow unchecked. This chart illustrates the impact of that predator behavior. Sea otters drive up living kelp biomass, resulting in an 8.7 teragram increase in carbon storage. At current market prices, that sequestered carbon is valued at up to $408 million. Hundreds of millions of dollars in natural climate mitigation are secured every day simply by a single species of predator eating its dinner. But when human activities like overfishing or hunting remove those apex predators from the coastal waters, the entire system fractures. Without otters keeping them in check, the purple sea urchin population explodes. In some areas of California, their numbers have spiked to 60 times the historical average. Starving and desperate, the urchins emerge from the rocks. They use specialized mouth plates to scrape the seafloor bare, eating straight through the holdfast, the heavy anchor point that tethers the kelp to the bottom. Once the stalk is severed from the rock, the plant is defenseless. Routine winter storms and wave disturbances easily wash the untethered giants out to sea. The habitat shifts rapidly into an urchin barren. These are desolate stretches of seafloor where up to 95% of the kelp canopy is wiped out, a state that can persist for decades. Removing a single predator triggers a systemic collapse that erases the physical forest and releases its stored carbon back into the system. Losing these habitats has planetary consequences. Because deep ocean temperatures remain relatively stable, healthy kelp forests act as climate refuges, providing a safe haven for marine life fleeing heat waves. Monitoring this crisis is an incredibly difficult task. Because they grow entirely underwater, most of these forests are invisible to standard satellite imagery. Scientists have to use specialized analyses of medium-resolution Landsat data to track the near-surface canopy, relying on artificial intelligence to separate natural storm damage from catastrophic urchin overgrazing. To truly measure the deep water damage and locate surviving climate refuges, researchers must physically explore the ocean floor using remotely operated vehicles. our ability to protect these massive carbon engines is currently bottlenecked by the simple technological struggle of finding them in the dark. Attempting to restore an urchin barren by simply replanting kelp is a futile effort, while the biological balance remains broken. Long-term preservation requires protecting the guardians of the forest. The sea otters, the local sharks, and the rays are what keep the herbivores in check. When these specific apex predator populations are protected and allowed to recover, the urchins retreat, and the barren seafloors successfully reverse back into thriving environments. Protecting the complex web of life that calls these forests home is the only way to ensure the survival of the forests themselves.